Imagine trying to verify the exact position and status of thousands of independent objects, all moving simultaneously across miles of open space. It's a classic systems problem. As the physical scale of a network expands, our ability to manually track the nodes within it breaks down entirely. In April of 1980, that system was the Boston Marathon. The 26.2-mile course is notorious for its grueling inclines, specifically a brutal half-mile stretch known as Heartbreak Hill that routinely weeds out hundreds of runners. Yet shortly after the legendary Bill Rodgers crossed the finish line first for the men, an unknown runner named Rosie Ruiz sprinted to the end. With a time of 2 hours and 31 minutes, she had seemingly just recorded the third fastest finish in women's marathon history. But anomalies immediately appeared. Ruiz wasn't sweating. She crossed the finish line of a major athletic event wearing a heavy running suit and open-toed sandals. And when a reporter asked how she trained through heavy interval regimens, she openly admitted she didn't know what an interval was. Ruiz had simply hopped onto the course near the very end. But her cheating exposed a massive vulnerability for the organizers. A marathon is a dynamic system of thousands of independent nodes. Without an automated, machine-readable data layer, policing every participant across 26 miles is practically impossible. The marathon organizers weren't the first to face this barrier. In 1959, the United States Railroad Network was facing its own tracking crisis. They had an inventory of nearly 1.6 million freight cars spread across the country, and on any given day, thousands of them were essentially lost in the system. This was a severe revenue drain. Companies needed to log the exact location of every car by midnight to bill correctly. But they relied on a 50-year-old method, workers standing in rail yards, manually writing down painted serial numbers as trains rolled by in the dark. A researcher named David Collins realized the manual approach had reached its physical limit. He set out to convert those painted horizontal serial numbers into a format that a machine could read automatically at high speeds. Collins approached the tracking crisis by isolating the variables of the rail system and treating each car as a discrete, readable node. He was utilizing modular systems thinking, a framework for identifying the invisible structures that dictate how a complex environment functions. To solve tracking failures, whether it's catching a fraudulent marathoner or locating a lost freight car, we have to break this mindset down to its first principles: modularity, dynamic scanning, and mechanism design. Modular systems thinking starts with the understanding that in any complex system, nothing is truly stationary, and every piece is linked. The behavior of the whole emerges from the precise relationships between its modules. We can trace this logic back to 18th century artillery. In 1732, the French military relied on the Valère 24-pounder cannon. It was powerful, but it was cast as a massive, static object. Moving it required 20 horses and dozens of men, entirely failing the mobility requirements of field warfare. In 1756, an engineer named Jean-Baptiste de Gribeauval redesigned the weapon from the ground up. He applied a concept called parameter variation. Instead of treating the cannon as one solid block, he isolated and tested individual components independently, like the elevation screw, the drawbelts, and the iron axle, while keeping the rest of the variables constant. He enforced strict manufacturing specifications, bringing measurement errors down to the thickness of a single sheet of paper. By standardizing these dimensions, a broken axle could be immediately swapped out on the battlefield with a perfectly identical replacement. The mathematician Pierre-Simon Laplace later codified this approach as a form of algebraic factoring. Gribeauval hadn't just built a new weapon, he had created a logical, physical syntax of interchangeable parts. That exact same modular logic rescued the U.S. Postal Service 2 centuries later. By 1950, they were drowning under a volume of 45 billion mail items. Human clerks, manually reading addresses, maxed out at sorting about 60 envelopes a minute. The solution was to modularize the country's geography. Assigning a 5-digit zip code transformed complex physical addresses into a standardized format. That one structural change allowed early automated machines to process 2,000 items a minute. Standardized physical modules only solve half the problem. For David Collins and his lost rail cars, the challenge was dynamic. He needed a way to bridge the gap between physical objects and a centralized data network using optical sensors. The constraints were severe. Freight cars came in completely different sizes. They rumbled past scanning stations at speeds up to 60 miles per hour, and the identification codes were printed in varying widths and reflective colors against dark backgrounds. Collins attacked the problem by defining what he called the primal design elements of an optical scanner, the core physics required to bounce a beam of white light off a moving target and decode the reflection. First was the code spot size, calculating the exact surface area where the light is projected and bounced back to the receptor. Second was the scan rate. If a train is moving at high speeds, the machine needs to sample the code hundreds of times per second to guarantee an accurate reading. And third was depth of field, establishing the maximum physical distance the sensor could reliably operate from the tracks, accounting for the varying widths of the railcars. Even with these parameters mapped, keeping a steady beam on a bouncing, speeding train was unreliable. The breakthrough came from a colleague, Frank Stites, who realized the horizontal layout of the serial numbers was the flaw. By turning the code sideways, converting it from a picket fence to a ladder rung style, they expanded the physical margin of error. Collins then engineered a system using rotating mirrors to sweep the light beam vertically. Instead of hoping a straight line of light perfectly intercepted a bouncing target, the sweeping motion ensured the sensor sliced through the entire vertical code pattern every single time. This optical logic laid the groundwork for modern automated identification. Once you can dynamically acquire data from a moving physical node, you eliminate the tracking blind spots. It's the exact same technological lineage of RFID chips and optical scanners that marathon organizers now use to verify that every runner actually runs the entire race. All of these solutions exist inside an engineer's true operating environment, the landscape of constraints and trade-offs. You can design an airplane with massive range, but the physical weight of the required fuel forces you to compromise on passenger capacity or cargo space. In the early 2000s, the city of Stockholm faced severe infrastructural gridlock. The conventional engineering approach would be to pour concrete and build more bridges, but constrained by geography, budgets, and historic architecture, physical expansion was no longer a viable option. The city brought in a team of engineers from IBM. They installed sensors, distributed 430,000 transponders, and analyzed 850,000 images to construct a comprehensive mathematical model of the city's traffic flow. The IBM team applied a concept called mechanism design, the branch of macroeconomics that functions like an engineering discipline. Instead of pouring concrete, they focused on constructing specific rules and incentives to achieve a predictable social outcome. The IBM team successfully argued for dynamic congestion pricing. By charging drivers a fee specifically during peak hours, they altered human behavior just enough to clear the bottleneck. When implemented, traffic volume dropped by up to 25%, restoring the city's public transport efficiency without building a single new road. This behavioral engineering scales across our modern infrastructure. It's the math powering Google Maps predicting a faster alternate route, or formulas developed by Marcel Boitois to balance national power grids by pricing electricity higher during evening demand spikes. At the core, it is the exact same logic. Whether you are maximizing the lethal efficiency of a modular cannon or maximizing the physical throughput of a city's road network, the optimization function remains identical. You are designing a mechanism to extract maximum utility from a constrained system. The logic used to manage 18th century cannons and 21st century traffic flow provides a framework for engaging with any complex system. These same rules of structure and constraint govern how we address challenges far removed from traditional manufacturing. This transdisciplinary mindset is embodied by systems engineer Guru Madhavan. Beginning his career designing medical devices and studying biomedical engineering at Stony Brook University, he eventually scaled that methodology up to address broad national crises. As a senior scholar at the National Academy of Engineering, Madhavan applies strict systems logic to issues like making prescription medicines affordable or architecting national strategies for cancer control. He uses what he calls systems consciousness to tackle wicked problems, massive multivariable societal challenges that completely resist simple, isolated technical fixes. The underlying truth of his work is that the precise rules governing data acquisition for railcars or parameter variation in artillery modules are the exact same tools we use to architect more equitable, functional social policies. This structural logic even governs how we construct art. The legendary director Alfred Hitchcock originally trained as an engineer, and he explicitly brought that mindset to the production of films like Psycho. Hitchcock famously argued that cinematic editing isn't actually cutting. Cutting implies severing something. To him, editing was assembly, the precise modular recombination of individual visual and audio elements to construct a highly functional psychological machine of suspense. We are moving into an era saturated by artificial intelligence and infinite oceans of data. But raw computational strength and processing power are not enough to solve our most critical bottlenecks. Navigating this landscape requires what Madhavan calls a culture of engineering. We need the rigorous, structural mindset, capable of looking at a sprawling, chaotic array of variables and organizing them into a unified, functional whole. Because in the ebb and flow of life, nothing is stationary and everything is inextricably linked. The ultimate task of the engineer is simply to find and build the invisible bridges between them.